the basis of the course. As I told you earlier, I'm preparing some notes which covered large part of the topics discussed during the lectures. So this will be the basic for the exam, but for sure not all the topics are there yet. So please keep track of the lectures and look at your notes as a first source of the information needed for the examination. I just share desktop. Okay. And did you have any problem in downloading the slides?
No.
No, okay, fine. So we start today continuing the discussion of variability of the ocean. But first of all, I want to revisit one slide of the previous lecture. You may remember we discussed a bit in detail the dynamics of the mixed layer for many reasons. It's important in mid-latitude. It's important as a main signature in terms of the seasonal variability. It's important also as a mediator between atmosphere and ocean interior. So as a quite important part of the ocean. And we model, well, there's a very famous slab model, vertically integrated model that takes the name from the two first proposers that are Krauss and Turner. In late 16, they proposed a very simple yet effective model that can follow and explain the dynamics of a shallow mixed layer under the forcing of the atmosphere and the mechanical steering due to the turbulent entrainment at the basis of the mixed layer. This is more or less the context. Here is a revised version of the slide. I found a typo in the previous one. There was a square which is wrong in the derivative of the temperature on the with respect of time here. But take the opportunity to look at the original paper, and I saw that this is much an easier way to formulate the model with less detail and more concepts. Essentially, the thermal energy equation is as it is, no changes. Here you have the change in due to the potential energy due to temperature is in the first term. The second one is the potential energy changes to entrainment in the second one. And you may remember that mixing means changing also deepening of the mixed layer means also changing the center of gravity. So adding temperature or deepening the mixed layer has an impact on the setting of the center of gravity of the mixed layer. And this means that the potential energy is also changing. This is similar to what has been written there. Now we have three terms instead of two. One is positive, is the wind mechanical energy input due to wind because of wind stress, because of other processes, but this is the input. And then you have mechanical dissipation that was connected to the friction velocity. And this is third term is the work against the thermal stratification, the large convective eddies that encompass the whole mixed layer are represented or parameterized here. So we have five terms instead of four, and here we have well differentiated the input of the wind and the turbulent dissipation of the mixed layer. So this is essentially clarification I like to do in order to clarify this important issue. This is just a modification, and this is here and not in the slide I sent you. So this is the right one. Okay. Okay, let's go. Up to now, we talked about the seasonal cycle, which is quite important. In mid-latitude, can explain from 80 to 90% of the total variability of the ocean condition, which is quite relevant in the Equatorial region. Probably the variability is less prominent. In polar area is even more sensitive to the seasonal cycle. But nevertheless, we have another mode of variability, which is important and essentially is the more tricky to capture, especially if you want to make a forecast, which is the interannal variability. Is the scale of variability is between 1 to 10 years. So you have a fluctuation, or you can find, often you find a fluctuation in the ocean properties that changes from year to year. So you have always the four seasons, but the intensity of the winter or intensity of the summer are different, the precipitation are different, the surface temperature are different, the mixed layer changes, and also the processes also change according to that. This year-to-year fluctuation is calculated with respect to the mean seasonal cycle. This is a concept for sure. The mean seasonal cycle doesn't exist per se, but it is a good starting point to subtract, which is the regular changes due to the regular changes in the forcing. And this year-to-year fluctuation is quite easy to find everywhere, is ubiquitous. And as a rule of thumb, this variability is related to the variability of the physical forcing, which has different time and space scale. Atmosphere has larger scale and is faster. Then this forcing creates a reaction, an adjustment by the ocean. It takes more time and is on a scale that typically are smaller. These two components are or may explain large part of the interannal variability of the ocean. We have two major examples of interannal variability that has a prominent importance, not only in oceanographic condition, but also in atmosphere, and also has important economical condition effects on the surrounding continents, as we will see more in detail in the following lecture, or later in the lecture, and also in the following one. The first one is the El Nino ENSO phenomenon. The second one is the Indian Ocean dipole. I would like to ask you, how many of you have ever heard already about El Nino? Have you ever heard?
Yeah.
Yeah. And do you remember what is it? No? Well, and if I ask you something about Indian Ocean Dipole? Well, nobody there. Okay. Go ahead. Okay. I think that we can have time to go into detail on that. Well, these two prominent or large-scale internal variability phenomena we'll discuss in detail in the next part of this lesson, but we can start looking at other pretty nice example of internal variability that can be detected by new or relatively new observational system that have been deployed in the last 20 years, such as the Argo floats that Miro has already explained you. Argo floats are the buoys that are free floating in the ocean, and now and then they take profile of the upper 1,000 meters, and they transmit this data via satellite to the data center spread around the world. So we have a very nice picture of the temperature, salinity, some biological, biochemical properties of the upper part of the ocean in a real time. This, say, observing systems, this are interrelated network of observation can take the pulse of the warming of the ocean, and this is quite clear in these two plates. The first plate is is the heat content of the global ocean from 60 to 2010, partly has been calculated with models, partly with the data, and in the recent part, the contribution of the Argo flows was quite relevant. And the same is plotted here, but the reference of the bottom reference of the upper layer is 2,000 meters. So we have the upper and the intermediate ocean average here. Both exhibits a clear heating. The black line is the only one, the black line is the dotted line, the two, they are, sorry, in black both, represent or show a clear increase of the heat content in the upper ocean. And this is a clear signature of the global warming that is taking place in a very quite prominent way. This is the major signal. However, you see that the lines are not constantly increasing. They are continuously perturbed by oscillation, stronger in the upper part of the ocean, somehow smoother in the deeper part when you integrate the heat content. The heat content, as you see here, is calculated as the integral of the density of the water multiplied by specific heat and the temperature measured along the on the water column. And the two indexes here are related to the limit of the integration, depth integration, and the temperature is calculated of the same way. So the most important formula for us is the first one. The two plates are here calculated in the North Atlantic only. And you see that the signal is present both in data or in data reconstructed in the data set reconstructed from the observation, but also the combination of model of data for the same period, same area, of similar results. Maybe there's a prominent anomaly here, but all the rest seems to replicate quite easily the trend. What is less evident is that the interannual variability, these wiggles here, seems not to be very well replicated in the model, well, and in the depth, in the deeper part of the ocean, while the special is for some data sets, the behavior of the upper part of the ocean is more realistic. My idea is the fact that the dynamics of the upper part of the ocean is easier to be modeled for many reasons, and the ocean interior tend to be less realistically reproduced by current states of art models. And this is another picture. In this case, is the recent, say, heat content in the ocean in the layer 0 to 1,000 meter, integrated over 10 years from 2006 to 2015. And we have plotted here in color the anomaly. So you see the standard reference for the ocean heat content in each pixel of the image, and you calculate the exchange or the changes in this period compared to the pristine quote-unquote state. So you make the difference of the recent data compared to the old one. And there are different data sets, but more or less the behavior here are quite similar. What we learn in terms of trend is the southern hemisphere, subtropical basin, tropical Indian Ocean have a positive trend. So the heating is ongoing, while subpolar, North Atlantic, subpolar, tropical, North Pacific has lost. And this could be related for the North Pacific to presence of El Nino related processes. And now we have an explanation. Well, we deserve an explanation for this interannual variability. And one, let's see, naive approach is to say we just see the direct effect or changing of the surface forcing propagated inside of the ocean because of diffusive processes. And you may remember that also in the theory of the main thermocline, that the diffusive approach is not enough energetic to be the major reason to explain the onset of this kind of permanent feature, large-scale feature in ocean interior. And here is again the diffusivity, even turbulent diffusion, is not energetic enough to transfer the signal from surface to ocean interior. And what is instead the candidate for explaining that is the fact that the interannual variability of ocean content is linked to the ocean water mass changes and connected to the formation. And during the last decade, or that decade, much of the interannual decadal warming is associated to the vast majority of the mode water. I just recall the mode water is the relatively homogeneous intermediate water masses that are formed in a specific area where the mixing depth is much higher than the surroundings. So this water, or the characteristic of the winter formation of these waters are the characteristics that are retained in the ocean interior. Changing the condition of the formation means that rapidly you transfer the signature also in ocean interior, and changing or cooling or warming the condition means that this water will retain the information of the in time, also when will be separated, will be stored below the upper part of the ocean. So there's sort of the adiabatic confinement of this water in the intermediate layer. As we saw, we have a couple of waters that are not heating as all the rest, but have different behavior. And this is, as I told you, is related to the volume changes of water masses, related to the isopeak heaving. So when the isopeaks rise, also the water masses change position and contribute to changing the volume and their characteristics. Okay. This is, to summarize, this is the global response to changes in the forcing fields mediated to ocean adjustment to the forcing. Here we have a more localized, more well, easy to explain, for example, example of interannual variability in South China Sea. South China Sea is a coastal sea that is limited by the China coast at west and Philippines here, and you have general circulation, which is predominantly wind force. And you have two seasons or two dominant seasons. One is winter, and the other one is summer. Is a mid-latitude basin. In winter, you have northeast wind blowing, and vice versa. You have the reversal, southwest summer monsoon that influence this basin during summer. Even if this switch is quite irregular, this is the seasonal cycle. The intensity of the two wind regime are not constant. And there is a recent paper that denied correlation to see how the SST, the surface temperature, change with respect of the seasonal cycle of the SST. So the SST anomaly calculated with respect to the seasonal cycle, and the surface height anomaly is changing with time, and how these changes can be correlated to other large-scale processes. And to do this, they do, the author of this study did an empirical orthogonal function analysis for this area in terms of temperature anomaly and surface height. And the principal component, you may remember, in the first lecture, we discussed a bit more into detail the UF, and every spatial pattern which evolve in time can be split in two parts. One is the spatial one, the other one is a temporal one, and the principal component is the temporal evolution of the UF, the overall signal obtained by the sum of a finite number of these modes, as UF are called, and their principal component that explain the time variability. So the time variability of the principal of the UF, or the dominant UF, dominant modes of variability for the temperature anomaly and the surface height, are highly correlated with the El Nino 3.4. What is the Nino 3.4? I don't say anything about now. I will explain later on, but please keep in mind that there are some large case processes happen in Equatorial Pacific that are correlation or a teleconnection with this kind of processes. How significant are these correlation? You know, correlation is, in my opinion, I'm a physicist and not a statistician, is not enough, it's not an explanation, it's just an evidence. But still, this evidence is quite striking. SSIH correlation is 99% with a 2-month lag. So the surface height is quite well, incredibly well correlated with the El Nino index, El Nino 3.4 index. Instead, also the anomaly of the surface temperature is very well correlated with the Nino 3.4 index, and the correlation index is 95%. The difference between the two is the fact that the correlation has reached its peaks at 8 months. So we have to wait 8 months to see the effect of the changing of the El Nino index. And this could be related to the fact that the surface height adjusts faster than the the temperature, which has much more memory, has a very strong thermal inertia, and takes time to adjust to a new condition. How this happened? This happened because the changes are not affected through the ocean circulation, but the changes are the time scale would be not enough to justify this, but the changes are fed into the system because of the changes of the atmospheric circulation. Atmospheric circulation changes according with the atmosphere, or is related to the changes that takes place into the Equatorial Pacific during the El Nino and Niña ENSO phenomenon. And they transfer this interannual variability into the upper part of the ocean. You see here, both variables that are considered are surface variable, surface height and sea surface temperature anomaly. And they are the two variables that react faster compared to the other. But still, we can say that changes and in one part of the ocean can be transferred via atmospheric mechanism in quite far separated areas, like coastal mid-latitude sea like South China Sea. And this is also an interesting part, also because the Chinese colleague published recently a lot on this in this area. So you have a very fresh, recent literature that cover this zone. And well, the previous example we saw the internal variability driven by changes in the forcing. Here we have different, also the area more or less the same. We are looking at the Luzon Strait between Formosa and the Philippines. And we have 4 plates here that show what has been found by a satellite analysis. And there are 2 different months. One is 2000, the other one is 2001. On the left side, you can find the geostrophic velocity calculated indirectly calculated by the surface height observation obtained by satellite. So you may calculate a velocity, making the hypothesis of a geostrophic balance, and the pressure gradient is essentially related to the differential or the gradient in the surface height. So this is not perfect, it's just an assumption, but it is quite interestingly related, or can explain quite well the presence of mesoscale or small scale structure that are present here. You see there are 2 numbers, 1, 2. The number 1 has an anticyclonic eddy. You see the arrows that goes clockwise here, and here a very nice shelf break front is the front that the current intensified and follow the shelf break, follow the topography. Looking at the 1 year later, you don't find it. They are totally disappeared. Instead, we have an eddy, again, more or less in the same position, but the direction or the vorticity is opposite. You have here a cyclonic eddy, and an analysis of the temperature, surface temperature map, confirmed this interpretation. You see here you have these two pattern has a warm signature compared to the water, surrounding water, and this is typical of the presence of these two pattern. Generally, the anticyclonic eddy has the core which is warm. They are called warm core eddies, while the cyclonic eddies are called cold core eddy, and this is perfectly matches the position of this eddy, matching much with the blue, very blue spot here. So we have a two different pattern and in the same season and in the same area, and this pattern are much smaller compared to the changes that could be expected by large-scale input due to wind. And this is explained essentially in terms of intrusion. So the presence of this pattern are not generated locally, but is are interpreted as the intrusion of the crucial boundary current, western boundary current that rims all the western side of the Pacific. And sometimes the Lucerne Strait is shallower. Sometimes this intrusion occurs in the central region of Lucerne Strait, and it results in an anticyclonic circulation. Instead, the intrusion changes the pathway and enter in the northern portion of the Lucerne Strait. And in that case, a cyclonic intrusion results. This has been detected and explained by Caruso et al. In quite recent papers, say about 15 years ago. It's no longer recent at all, but okay. And as I told you, we saw in the picture, this is quite evident in the winter season for many reasons. One of them is the fact that we have a clear evidence of the surface temperature that in winter is lower than the surroundings. So the temperature signature is more evident than in the other period. The first, you remember earlier, we saw that the wind regime can change or modulate the seasonal pattern, especially the temperature and the surface height. Here you have a structure. It's also surface temperature, but we have a structure which is fully 3D. We talk about eddies, so there are 3D patterns that are generated outside the basin and are advected by an intrusion of a coastal, western boundary current, very important western boundary current that enter in different area of this region of the Lucerne Strait into the coastal southern China Sea basin. So in this case, the remote control takes place through advection instead to changes in force. So this is another example of seasonal variability. Then we have another interesting interannual variability in North Atlantic. We have North Atlantic is the ocean which is more traditionally more investigated. We have more data, and possibly we have also more studies about that. And also here, an interannual oscillation along the north. You know, the Gulf Stream is the boundary current, western boundary current that goes from the tropics up to the northern part of Europe, and is clearly identified by warmer water compared to the rest, and is responsible to the meridional heat flow, heat transport that well makes the Northern Europe region warmer and more pleasant than the counterpart in the America. So it's quite important the role of Gulf Stream in terms of oceanographic point of view, but also in terms of climate, is quite important. And there are interannual oscillation in the front that separates Gulf Stream to the surrounding water. And this has been detected as usually in sea surface temperature, because you have a lot of data from satellite with this for this variable, and this means that we have sound observational basis to do this kind of pretty long-term analysis. In situ measurement cannot give you the same detail and the same of accuracy in the reproduction of this variability. So we are constrained to use SST as a proxy of changes, but most probably this means that you have more changes also in depth and not only confined the surface. But the data are there. And what the data teaches? 7-8 year oscillatory mode characterize the basin-wide southwestern to east-oriented propagation pattern of a SST field. So there are an oscillation along the direction southwest to northeast. And this is not a natural oscillation, but is forced. As usually, this is forced by the meridional oscillation in the meridional dipole structure of the zonal wind stress forcing. You see in the plate, this is the SST related to the, so it is the signature, the Gulf Stream here, and then which finally reaching the north-east western side of Europe, the UK and Ireland here. And then you have the dipole in the tau x. Tau x is the zonal wind stress, and you have a positive here, -1, and you have strong shear. And in the subpolar gyre here, SST and tau x fields are in phase opposition. The stronger tau x is, the cooler is the SST. And this, well, not very difficult to relate the two, thinking that when you have strong wind stress, then you have a cooling of the upper ocean layer. We'll have just learned about something about Krauss-Turner conceptual model or slab model. And we remember that the cooling means that you have evaporation and you have steering, and you have entrainment. So when you have a strong wind stress, the mist layer goes experience a cooling. And this is something that we can, well, this approach can be applied also here to explain this variability. So again, the variability here is not an internal variability, but is forced by changes in the interannual the interannual changes of the forcing field in the zonal wind stress in the subpolar area. So we are just but some example of that. There are other, for example, in the heat content in southern hemisphere near New Zealand. Again, there are complex interaction between the coastal processes, the adjustment of the thermocline, and the wind regime. In Mediterranean, we have other processes that takes place, always connected to the variability, to the storm tracks, to the changes in evaporation. There are variability connected to internal adjustment processes, semi-oscillations in subbasin, and so on. So whenever you go and whenever you have enough data, you can always detect some trends. For example, the heating is almost ubiquitous. Some regions are not experiencing that, but a large part of the world are warming fast. But this is not constant. We have continuous oscillation of that. And interannual variability can explain that. It also can explain the fact that sometimes you have an increase in the warming speed, and sometimes you have a decrease, or are even stopping the trend. But when the scale is long enough, the trend, the heating trend, the warming trend is always the major and undisputable signal present. So we can make a short recap of the internal variability examples. So we saw that the changes in ocean heat content is connected to the adiabatic adjustment of wind-driven circulation. The changes of the SST and the surface height in South China Sea is connected to the changes in the wind regime related to the El Nino phase. The internal variability of a recurrent eddy in proximity of Luzon Strait due to the vorticity reversal or the polarity of the eddy, which is connected to the advection through the vorticity by the Kuroshio current. And oscillation in the Gulf Stream front is related to the variability or internal variability in the zonal wind stress. Internal variability has the characteristic to be driven by external forcing and does not exhibit a strict regularity. This is not an oscillator, it is just a response that depends on what happens outside and is not as regular as the seasonal cycle. Now we go a bit more into detail to the probably the most important and more studied process for that has this time scale. And this is a subject that is discussed often also in atmosphere courses and as in ocean courses, because the two the explanation for such kind of phenomenon cannot be limited to ocean or atmosphere alone, but is the coupling between the two that can explain that. However, since this is an oceanography course, we are more and more interested in the oceanographic aspect instead of the atmospheric part. Okay. We are talking about El Nino and La Niña, and in this big plate has two very nice sea surface temperature anomaly. As you may remember, the anomaly is the difference of this year compared to the climatology for that month. So we have an average December that and the data corresponding to December 88 are subtracted from the average, and we see here the anomaly. So this cold tongue that replenished the whole Equatorial Pacific is called, or is the prominent signature of La Niña. If you have a blue tongue here, this is La Niña, full stop. And in December 1997, almost 10 years later, we have in the same position a strong red tongue. And this is called El Nino. And if you look at the variability and for the rest of the ocean, there are just small or slight differences compared to these two processes, which are dominant and, as we'll see, are not local. So what is happening here is so energetic. It has the capability to influence via remote teleconnection vast part of the area in the Pacific, but not only there. And this is an evidence that is not new. So we can say that traditionally, the fishermen off the coast of Peru has been aware of the fact that from now and then, unusually warm water in late autumn, early winter would reduce the catches of anchovies, other fish. So they were very well aware of the presence of this phenomenon, and since the effect of this phenomenon was often began near Christmas time, this phenomenon was dubbed El Niño. That means the Christ child in Spanish. And but until the 1960s, nobody related this local process to largest mode of variability of the area. And Jakob Bjerknes, Norwegian oceanographer and meteorologist, was the first to recognize that El Nino is related to a recurrent regional atmospheric anomaly, which is called southern oscillation. So we have ocean part and also an atmospheric part. They are coupled. The combination of the two phenomena are called El Nino Southern Oscillation. So ENSO is the nickname or the acronym that is used to identify both of them. As I told you, we'll be more interested in the oceanographic component than the atmospheric part. But only looking in its full complexity that we can shed some light on the dynamical mechanism that can explain the quasi-periodic phenomenon that links ocean with atmosphere. We'll see that this is not an oscillator. So one stage, one El Nino doesn't mean that automatically you should have the condition prone to give La Nina after a couple of years. There seems to be decoupled. You have El Nino, you have La Nina, even though in my knowledge, you don't have two El Nino, one after the other, and maybe, I don't know, but generally I saw that you have El Nino, La Nina, El Nino, La Nina, and oscillation in this sense. But the two are not dynamically related. I told you that the southern oscillation is responsible for or can be responsible for the El Nino and La Nina, or relate, more than responsible, can be interlaced with the El Nino La Nina processes. And it's interesting to understand how southern oscillation has been found. Sir Gilbert Walker is a meteorologist of the British Imperial Met Office, was sent in the first early 19th in India, to study the recurrent droughts that takes place in that country, and try to understand the motivation for that. And him looking at the data available, we saw that there is a prominent variability in the pressure in Tahiti, which is located in French Polynesia, in the middle of the Pacific, Darwin, which is located on the eastern coast of Australia. And this index, which is just is shown in the plate here, has a quite clear interannual variability, and the index shows a striking consistency between the abnormally high pressure and drought in Australia and low pressure increased precipitation of a Polynesian island of Central Pacific. And this index somehow represents the effect of the Walker cell. Is the atmospheric cell that takes the name of, obviously, from his discoverer, that essentially is always active and along the equatorial region of the Earth, you see here. And since this is atmosphere, it's not my field, I'm just very cautious in going to detail, but
some details should be done. This is the area of the Pacific. You see in dotted, is dotted here. And the Walker cell changes and has different circulation during the different conditions that La Nina and El Nino. So Walker cell is larger and start from the Peru coast and reach Australia. You have strong trade wind blowing westward. You have warm water here. You have clouds, rain on the Australia. The stronger the trade wind, the stronger these atmospheric processes, and the convective cloud bring water which is now dry, and the counter current aloft the trade wind goes eastward, and this area is fairly dry in the eastern part, and the circle closed. This is the Walker cell in La Nina condition. In El Nino, have normal condition. It probably is not far much different. Again, you have trade winds, you have convective clouds, dry air going back to close the loop, and then you can, the third possibility, then which is anomaly, and that are found in El Nino, and which the low pressure are moved in the central ocean Pacific. Here you have the rain, you have the convective clouds, and you can have two, not one, two Walker cell. And in this case, the trade wind even weaken, even can reverse on the western part, and the things change. And the Walker cell is sustained because of SST and heating of the continental region. SST as a gradient, we see better in detail, and heating is also the solar heating on this area is much on land is much more effective than ocean, which has higher thermal capacity, changes much less than land. And so we just observe this. We observe that the Walker cell exists and have three different behavior. We will discuss more in detail La Nina and El Nino, which are the two extreme. But three are exhibit more or less the same kind of atmospheric circulation. They are connected to the changes of the closure of the loop, which move from Australia up to the central Pacific, and this has an important effect on trade winds intensity and even in trade winds direction. Okay, let's start from to discuss also the atmospheric, the oceanographic implication and phenomenology that can be found during non-El Nino condition in Equatorial Pacific. And typically, in non-El Nino condition, we have a very nice Walker cell we saw before. And here is depicted by the fact that we have these arrows, the strong arrows, means strong wind. This is a trade wind and flowing westward across the tropical Pacific. Coriolis is 0, so here you don't have any deflection of the wind that goes from high pressure to low pressure straight along the fastest path, so that connect the 2 points. For the same reason, the wind stress drags also the surface water, which is advected toward the Western Pacific. And you see that the temperature here in the western part is higher than here. Why? Because of this drag, for continuity, dense water is sucked in the surface in the eastern part here. This is partly true, partly is due to the fact that the thermocline is shallower here, and this upwelling is more effective here because the buoyancy force is as less effective here, and so the uplift of dense water is energetically more convenient in this area. When you have this condition, so cold water here, warmer water here, and upwelling this area, we are talking about La Nina period. If you remember the first image, the first plate with the sea surface temperature anomaly, La Nina was identified by very cold, surface temperature tongue in Equatorial. This is the connection with the forcing and the ocean response for it. Obviously, when you're pushing water warmer there, and they are confined in the western water pool, this western water pool gets warmer and warmer, and this makes the thermocline even deeper here in the western equatorial Pacific. This warm pool has the net effect to warm, to exchange heat fluxes to atmosphere, and convection and precipitation increase. This as the thermodynamic engine of the Walker cell is closed by a higher in atmosphere. The prevailing wind is blowing eastward and close the loop. So here we have, you see here, Walker cell. Now here we have the equatorial thermocline, which is deeper. It is a pool of warm water, a pool of thermal energy that is exchanged with atmosphere. The atmosphere heats, moisture is abundant, and when you have a lot of rain, then you have drier air going eastward to close Walker cell and aloft the strong trade wind that continues blowing this way. Obviously, this density gradient is counterbalanced by the wind drag, and this system is in a sort of steady state. What happens instead when you are looking at El Nino condition? Well, everything starts when the SST of the eastern tropical Pacific rises sensibly in a very narrow zonal band, roughly determined by 5 degree north, 5 degree south. So there is quite an equatorial band, and this increase of the SST is essentially more evident in area from the day line, which is this one, is the line where the date changes, up to the Peru coast. In the western part, it doesn't change that much. This is the first signature. As we saw, the overlying winds and atmospheric pressure reacts to changes in SST. And this means that you have a convective area here, and you have the Walker cell that is less effective. The temperature gradient is less well developed according with La Nina, and so the Walker circulation is still active, but less energetic. And in the eastern part, western part, we have again an area or a large area where the convective processes are effective. You have rains, and the wind is, or the trade wind will reduce, or even can change direction to close this small Walker cell in this area. So we have this anomalous Walker cell circulation, and the major or clear effect is the fact the convective region is displaced across the day line and not along the Australian coast as before, as during La Nina condition. Obviously, you have warming here, and we have a reduced upwelling of cold water along the equatorial coast of South America. So the thermocline is somehow released and deepened. And the trade winds are weakened again, and they shift progressively or leave the warm pool farther eastward along the convection and precipitation areas. So the warm pool is somehow related and is the origin of this convection in atmosphere. And there is an adjustment of the warm pool in along the equatorial line due to also the wind, the changed wind regime. These are the El Nino conditions. So equatorial thermocline is always deep. The convective part of the Walker cell are displaced in the middle of the Pacific across the day line, and the warm water pool is displaced in the center part of Pacific. In practice, the most also for practical reason, the most evident signal in the coastal area is the deepening of the thermocline in along the Peruvian coast. You can see here there are two 3D representation of a slab in located around the equator from Peru to the Australia, and here you have a case of La Nina. This is the El Nino case, And this is the scale of temperature between 7, which is the ocean interior temperature, until 31 is the surface temperature. The scale is the same. And you see, during La Nina, you can look at the thermocline as this narrow green-yellow band. There's a transition from surface to deep water. This is quite shallow. There's an amplification surface height anomaly, but what we are looking for is this one, is the fact that essentially the dense water are more or less in contact with the central part of this cold tongue that is characteristic of La Nina. A few months later, when we have or earlier, when El Nino was present, the condition here was substantially different. This green transition band is much deeper, and there is no longer any connection between the ocean interior to the surface, and no signature, no temperature signature due to the upwelling of deep water into the surface layer. And so this is we call it unusual, but it's usual during the Nino event. Sometimes this event is stronger, sometimes it's less, but Nino is always related to the deepening of the thermocline, and this decouple when you have this warm water which are depleted of nutrients because there are surface water that are piled up on the eastern part of the coastal Equatorial Pacific, and you have the coupling of the surface water, so you don't have a nutrient anymore there, and this has an impact on the productivity of the area. And sometimes the thermocline here can dip as far as 150 meters along the Peru coast. So you are in a sort of desert. That's why you don't have any more anchovies and other fishes available because they don't have enough food to eat. It's worth noting that the upwelling is quite clear in La Nina. It's not only it takes place only as a coastal upwelling here, and but also all along his pathway here, the surface water experience an upwelling all along their path toward the western part of the Pacific. And this can be explained in terms of also of the Ekman transport in the Equatorial region. This is a very, very well-known process. It's something which is often idealized as in this cartoon. You have the surface wind blowing in the narrow equatorial band between 5 north, 5 south latitude. The surface wind is the trade wind blowing this way, westward. And because of Coriolis, you may remember on the theory of Ekman layer, we have a net Ekman transport at 90 degrees, so northward Ekman transport of the water, which are slightly outside the equatorial itself. In the southern hemisphere, you have the same process, but because of changes of polarity of the Coriolis coefficient, the Ekman transport goes in the opposite side. So it goes southward. So you have the same forcing, the trade wind. North the equator, the Ekman transport goes northward. South the equator, the Ekman transport goes southward. So you see the second plate, the water are in the surface layer are displaced and they suck up the thermocline, and the cold water, relative cold water, is brought to the surface. This is a very, is an effective equatorial upwelling during, not related to the coast. Well, this is very nice. Unfortunately, this idealized picture is rarely present because a variety of reasons, or as easterly winds maybe not strong enough, or they have continent. And in the Equatorial Pacific during the La Nina year, they have an effect and can be detected. This is one of the motivation because El Nino and Niña takes place there and not in other parts of the world. Because, and as we saw in the data shown before in the 3D data, this process could be effective. And how frequent happened El Nino? Well, we can say that El Nino takes place every 7 years with different intensity. So even if the process is quite well established, we know how the things go. At least we have a conceptual model that is able to explain that quite well. But we have no certainty on the intensity of El Nino changes. And to call an event El Nino, you may remember that in El Nino area we have also a seasonal variability. And to have a real El Nino, which is a sensitive one, we should have at least 0.5 degrees Celsius of anomaly of the surface temperature or more, and a duration longer than 6 months. So we have to go farther, go beyond the typical seasonal variability, and the temperature should be slightly higher than the usual one. But generally, this number could be much more higher. For example, one of the most energetic El Nino events during 1982-23, SST in the Eastern Tropical Pacific was from 5 to 10 degrees above normal. So something which is absolutely astonishing, looking at the other natural variability of the ocean. El Nino changes in time, changes in intensity. So sometimes changes in shape. The meteorologists called flavors this different wave of taking place by El Nino. El Nino change also position of the sea surface temperature positioning of the anomaly in Central and in Eastern Pacific. This is called Modoki El Nino, or Modoki in Japanese is similar but not equal. Is resemble a Nino, but it's not a proper Nino. This is not clearly or totally well established, but the message is even if the process is more or less always the same, we can have change in frequency, change in intensity, a change even in the spatial pattern. Why we have this strong interest in El Nino and La Nina? And there is a huge amount of studies that are look at the teleconnection between this important volatility mode of the tropical Pacific and changes of weather in vast part of the world. And the most well-known and well observed impact is the dramatic decrease in field catches with in Ecuador and Peruvian, which are largely based on, or the economies of the coast economies are largely based on the fishery, and so this has a devastating impacts on their economy and the society. But also in this area, you can have a lot of rainfall increase, which can be dangerous because you have erosion and floods in the same areas. Sometimes you can have droughts, for example, in Australia, or large, especially with El Nino, large drought and severe changes in weather in a vast part of the area around the Pacific. If you look at here, the El Nino impact has a large part of warm, the red spots, which means they're cold, warmer than usual, and also wet area. Here we have dry, but for example, in China we have blue spots, so colder than usual. But even in Africa, the dry condition can be related to El Nino. Similar, but the reverse sign is La Nina. This is not my field. I don't want to go into the field. What is important, keep in mind that the El Nino or the ENSO is not a local process, but is has an important effect also on the global weather and seasonal variability at a global scale. Okay, this is more or less what I want to show you for today. And if I don't have, you don't have, okay, question, I stop here. Okay. Any question, or if you have doubts or whatever you want, you can reach me by email, and then we can discuss maybe on next during next, or I can answer you writing something. And if you don't have, if everything is clear and you're happy with that, we can meet again the day after tomorrow, same time, same place. Okay.